Alright, so this is a two-dimensional kinematic problem, otherwise known as a projectile motion problem, and it's going to involve constant acceleration. That would be the constant acceleration due to gravity. And so let's read the problem. Because of your knowledge of physics, you've been hired as a consultant for a new James Bond movie called Oldfinger. In one scene, Bond jumps horizontally off the top of a cliff to escape a villain. To make the stunt more dramatic, the cliff has a horizontal ledge a distance h beneath the top of the cliff, which extends a distance l from the vertical face of the cliff. The stunt coordinator wants you to determine the minimum horizontal speed in terms of L and H with which Bond must jump so that he misses the ledge. So here we have a situation where we have a projectile moving off the top of a cliff, and its initial velocity is going to be perfectly horizontal. And we want to know the least amount of horizontal speed that James Bond's going to need so that by the time he falls a distance h from the edge of the cliff, he has moved L meters away from the cliff so that he clears the ledge below. So now let's look at this again, reread the problem, and see what values we can pull out of this that we need to use in coming up with our solution. So we know that he's going to be jumping horizontally with some initial speed, and that we want to determine L and H and their influence on that speed. That is, we want to find the initial velocity he'll need with a given ledge width L and height that he's going to fall H. So let's take our slide and push it off to the side real quick. So we'll keep it visible, but we'll get it out of the way. And get my pen tool. So now let's draw our cliff so we can get a sense for what this problem is going to look like. And here's our ground. And let's say there's water down here, and he's going to fall into the water, but he has to miss the ledge that is protruding out from the side of the cliff. There we go. So we'll call this ledge distance from here to here length L, and we're going to represent James Bond as a circle at the top here, and he's going to begin with just an initial velocity in the x direction. His initial y velocity is going to equal 0 because he's going to begin, we'll say meters per second, because he's going to begin at rest with respect to the vertical, and he'll be running at a constant velocity off the edge of the cliff, and that is the variable that we ultimately want to know. And then we're going to call this height here, from where he jumps to the base of the cliff, we're going to say that that is height h. So we're going to determine how height h and length L all come into play when he jumps at that velocity off the edge of the cliff, where he'll produce a parabola that looks something like this, hopefully, as long as he clears that cliff. Alright, so now let's clean up our drawing, and that way we can go about solving this problem. So we'll go back to having our James Bond character. Here he is. We'll put him at the top of the cliff, and just so we understand what kind of motion we're talking about here, we'll draw his the parabolic path that he would make. Let's do that here. Try to make this a dotted line. And we're going to assume he's going to clear it by, let's make that a little bit smaller, actually. There we are, and we want to find the initial velocity in the x direction, and we'll write down some of our other givens. We know that Vy is equal to 0 meters per second, and we know that the acceleration due to gravity is 9.8 meters per second squared, and we're going to have a variable that we're calling L, which equals the ledge length. We'll just say ledge. And we're also dealing with a height h that James Bond is going to fall before we find out whether or not he clears the ledge. Let's also write down some of our kinematic equations that we're likely going to use. We know that we're dealing with velocity in the x direction, which is a constant velocity, so that's going to be distance over time. And we also know that we have acceleration in the y direction, so our formulas in that regard are going to be, let's say we have Vf equals Vi plus Gt. We also have Vf squared equals Vi squared plus 2G, and we'll call that h for height, the height you would fall. We could also call that y. And we also have a range formula, which looks like this: y equals any initial displacement plus VIT plus 1/2 GT squared. Alright, now let's give ourselves a little more space by shrinking this down, putting it off to the side so we could still see everything. Now we know that it's the velocity in the x direction that's needed, and that is equal to the distance that James is going to travel divided by the time it takes. And the distance that James Bond has to travel, this x variable right there, this variable, is the same distance that he has to clear in order to safely pass that ledge. So we're going to call that distance L. So really it's the initial velocity in the x direction is going to be that distance L over t. That is, he has to travel this far in the horizontal direction in this amount of time so that he doesn't hit this ledge over here. So he has to go far enough this way so that by the time he falls down to this height here, he has made it this far following this path. If he isn't moving fast enough in the time it takes him to fall this distance, he'll hit the ledge. So he needs to be going some minimum velocity to clear this distance in this amount of time. So that's how we're going to approach this problem. So since this is ultimately what we want to find, we need to have these other values. Now we know that L is a value that's going to be given. We can plug in some ledge width and find out how fast we need to be moving in order to, in this amount of time, make it safely this distance. So this is important information we're going to hold on to. We'll stick this up here. And again, we want to find, now this is a given value, this ledge width. We want to find the amount of time it's going to take for James Bond to fall this distance. So if we know what this distance is, we can determine how much time it takes and then see that we're going fast enough in order to cover that ledge width. So what factors are going to be important in determining the time it takes to fall a particular distance? Well, clearly we'll want to know that distance, which we're going to call h, and we're also going to want to know the rate at which something's going to speed up as it falls through that distance during that amount of time, and we know that value is g, 9.81, or we'll just say 9.8 meters per second squared. And we also know that the initial velocity in the y direction is 0 meters per second, because with respect to the vertical, as the James Bond runs off the cliff, he is only moving horizontally. His initial velocity in the y direction is 0. So do we have a formula that involves the time it takes for something to fall, the height it takes for something to fall, the rate of acceleration due to gravity, and if we need it, an initial velocity even though it's 0? And so we'll look back at our kinematic equations and see if there's any here that involve these. And I'm looking here at this range equation, or this height equation, and it says that the distance I fall, plus or minus any initial distance, is equal to the initial velocity times the amount of time that you're falling, plus 1/2 times g, the rate of acceleration, times t squared. That's that same time variable. We also know, so here let's write that. We have y equals, we know there's no initial displacement, so we don't have to worry about that. We also know that because our initial velocity is 0, we don't have to worry about that term. So really we have y equals 1/2 g t squared. And so you can see we have most of these variables. We have y, that's what we're calling height, so we'll change that. 1/2 is a constant, g is a constant, and t is what we're looking for. So we can rearrange this formula to solve for t. So if we can make some room on our board. Ooh, that's goofy. Let's make some room and see if we can solve this problem. Most of that's still visible except the original question. So let's rewrite this equation here in terms of t. So we will multiply both sides by 2 to get 2y equals gt squared, and then we'll divide both sides by g to get t squared by itself, and that'll cross out those g's. And then what we'll do is take the square root of both sides. So our final equation is going to look like this. We're going to have t equals the square root of 2y over g. Oh, and you know when we said that we would make y h to reflect that h is the variable that represents the vertical height. So we'll say that t equals the square root of 2h over g. That's the square root of 2 times the height that James Bond is going to fall divided by the rate of acceleration due to gravity, and all of this whole expression is under the radical that you see there, not just the 2h. Well, we're nearly finished. Let's make a little more room and solve for our final variable, velocity in the x direction. And so we'll say that we know the velocity in the x direction is going to be equal to the required velocity in the x direction is going to be the ledge width that he needs to clear over the time it will take to fall that given height. And we also established that the time it will take is equal to the square root of 2 times the height over gravity. And so our final equation is going to look like this. We're going to say velocity in the x direction is equal to L, the ledge width, divided by the square root of 2 times the height he's going to fall, divided by g. Now let's see what that looks like. Let's make up some numbers and see what kind of velocity he'll need to have in order to clear a certain ledge if he falls a certain height. So let's suppose that he's going to run off the cliff, and that he's going to fall a height. We'll say that he falls, 25 meters. And as he falls 25 meters, he's moving in the x direction at a particular constant velocity, and the ledge he needs to clear, let's say that is 10 meters wide. So he has to fall 25 meters while moving in the x direction at this velocity, and he's going to fall after these 25 meters, hopefully clear a ledge that is 10 meters out from the cliff. So that's going to look like this. We're going to say that make some room here, velocity is equal to this 10 meters divided by the square root of 2 times 25 meters all over the acceleration due to gravity. Alright, so the velocity is going to be, changing color there, 10 meters over, let's see, 2 times 25 is 50, and if we estimate that g is 10 rather than 9.8, we have 50 divided by 10, which gives us 5. Square root of 5 is like 2.2, so 2.2 seconds. So the velocity is going to be 10 over 2.2, and so the velocity in the x direction that is required to clear the 10-meter ledge after falling for 25 meters is 4.5 meters per second. So James Bond needs to be running at a rate of 4.5 meters per second in order to clear the 10-meter wide ledge after he falls for 25 meters. Well, there you go. And as we finish up, I'm just going to scroll back through all of the work that we've done so you could take a look at it. And there's where we began with taking a look at our initial kinematic formulas, the givens, looking at our sketch, and there was some more detail on that sketch before we continued on, and the original problem. Well, there you go.